Hi, welcome back to this course on computational thermodynamics and kinetics of materials. We'll continue with Gibbs energy versus composition lots more in this class. These are the contents. We'll see how Gibbs energy versus composition plots change as temperature changes, and we'll see how to see the mathematical descriptions of these Gibbs energy curves. And we'll see what is Gibbs energy composition plots with respect to different reference states, and how the curves look for stoichiometric and non-stoichiometric compounds, and how Gibbs energy minimization and mu equalization are same. This is where we left last class, where we have identified that a phase diagram could come from Gibbs energy versus composition plots at different temperatures. Okay, how is the temperature dependency of Gibbs energy? This is a curve we have seen for pure aluminum, a single phase, single element, where Gibbs energy versus composition for two different phases, liquid and solid, were plotted against temperature, and both the values, Gibbs energies of solid and liquid, both of them decrease with temperature, decrease with increase in temperature, but the liquid phase values, Gibbs energy values, decrease faster compared to solid. Eventually, this is the reason why they intersect, and there is a melting point coming beyond which only liquid becomes stable and below which only solid is stable. Right? So G of liquid decreases at a higher rate than that of FCC with increase in temperature. This is what we have seen for single elements. So we are going to consider three different temperatures, T1, T2 and T3. T3 is the highest. And how AB binary system behaves, the Gibbs energy versus composition plots of solid and liquid phases in this system behave with respect to these different temperatures. We have seen these curves previously, but you have to see how is the magnitude changing with respect to temperature here. You see both of the Gibbs energies decrease as the temperature increases, but the liquid's value decrease at a higher rate. Therefore, eventually the liquid which is not stable throughout the composition at some lower temperature becomes the only stable phase at higher temperature throughout the entire composition. So it is overtaking the solids curve. Okay, so solid is also decreasing, liquid is also decreasing. Liquid decreases at a faster rate, eventually becoming stable at high temperature. This is only the rate at which the curves move, but the shapes also will change. You will see that in this class. So G versus X plots of different phases change differently with respect to temperature. This is one of the reasons we get so much of variations in the phase diagrams, because of these differences in the Gibbs energies. So we'll see more about that little later. Before going there, we will understand how the Gibbs energy descriptions are, basically the mathematical representation of these curves. So we have seen Gibbs energy versus composition plots coming from pure element Ga, Gb curves and mechanical mixture line like this. So this is just before mixing. Take any composition, and that G of mechanical mixture can be represented like this mathematically, XaGa plus XbGb. And once the solution forms, we can talk about Gibbs energy of the solution, XaGa plus XbGb plus a mixing Gibbs energy will be added. The difference between these two lines is the Gibbs energy of mixing, and this entire thing is at constant temperature and pressure. Right? So here the mathematical representation is Gibbs energy is a function of composition at constant temperature and pressure. Right? But when we want Gibbs energy also as function of temperature, we have just seen in the previous slide that Gibbs energy is quite different. Gibbs energy of different phases change differently with respect to temperature. So we need Gibbs energy as a function of at least two things, composition and temperature, if not pressure. If pressure dependency of Gibbs energy is also available, it is well and good, but at least we need Gibbs energy as a function of composition and temperature. So we need the mathematical description, basically equations for these different curves. And you know what we can do if the curves are available, at least one use you know now, that we can make phase diagrams out of it. Right. So to understand that Gibbs energy description, let us start with the ideal mixing solution now. So if it is the ideal mixing solution, we will add only delta G mix ideal, which is this curve now. If we take some overall composition, this is the mechanical mixture Gibbs energy, this is the Gibbs energy of this ideal solution. So the difference between them is the Gibbs energy of mixing in ideal solution. We have seen this already. Gibbs energy of non-ideal solution will be deviated from this. Okay. So should we consider this delta G mix ideal or not? If we want to calculate Gibbs energy of non-ideal mixing, we will consider this because the tendency for the elements to mix, that's the Gibbs energy of mixing in ideal case, right? Without any interaction itself, elements will try to mix. That tendency is always going to be there. That entropy of mixing is always going to be there. Only thing, the interactions, whether the elements like each other or not, that is going to play an important role now. That is going to deviate the system from its ideal mixing. Yes, therefore, we'll put a curve. This is a non-ideal mixing curve. This is basically a solution of non-ideal nature, and its Gibbs energy is represented like this. It is deviated from the ideal curve by this much. At this composition, we call this delta G mix E, which stands for XS. Okay, XAGA plus XBGB plus del G mix ideal from plus deviation from the ideality, that is delta G mix E. It is excess Gibbs energy, basically accounting for deviation from ideality. What it takes care is the chemical interaction effects, whether elements like each other or dislike each other. Based on that, how the enthalpy is changing, how the entropy will be changing, those effects are considered in this chemical interaction effects. Apart from this, we can also add any physical, for example, any magnetic contribution because of magnetism if there is a Gibbs energy change, or because of any stress or pressure effects if there is a Gibbs energy change. They all can be added just like this to the Gibbs energy, so that we can consider any effect in this Gibbs energy description itself. Should the Gibbs energy composition curves look only like this for a non-ideal case? Need not be. There can be different shapes like this. For example, this is some gamma phase, it has this kind of curve. This is some sigma phase, it has this kind of curve. Meaning, with respect to composition, the Gibbs energy can vary for different phases in n number of ways. Okay, G of different phases change at different rates with respect to composition. This is an important conclusion. Let's go back to this Gibbs energy description that we made with the excess Gibbs energy of mixing. This part here, the first two terms in this equation, they are reference state Gibbs energy, right? And this part here, ideal mixing Gibbs energy, is nothing but minus T delta S mix ideal, basically the configurational entropy of mixing with the ideal mixing case. There is no enthalpy of mixing when we say ideal, therefore only minus T delta S mix is the ideal mixing term. What about the third term? This third term has delta H mix minus T delta S mix excess, meaning any other entropy contributions or deviation from ideal mixing will be here. This term is often ignored, but it can be significant depending on the system. You need to keep that in mind. So if it is ignored, we can write this equation like this: G reference minus T delta S mix ideal plus delta H mix. This is how Gibbs energy of a phase is represented. Okay. G, reference state G plus delta H minus T delta S. Delta H mix minus T delta S mix ideal is the delta G mix. We will see some example cases how it looks. If this is the delta G mix value, delta H mix is like this, let's say, and T delta S mix is going to look like this. It's delta S mix is also always a positive quantity. Delta S mix ideal is always a positive quantity. Multiply that with minus T, you are going to get a negative value throughout, and it's going to be symmetric. You know the formula for it, minus R XA ln XA plus XB ln XB. So that is going to give us this curve, and when this curve minus T delta S mix ideal and delta H mix are added, we are going to get delta G mix, and it's going to look like this because of this competition between positive enthalpy of mixing. This is all positive here, and this negative value of ideal Gibbs energy of mixing, right? If you go to a temperature which is higher than T1, okay, let's say it's quite high, therefore when it is multiplied with this delta S term, minus T2 delta S mix ideal becomes a large negative value like this. When that happens, it can dominate completely over this delta H mix and make the entire delta G negative. You see here delta G actually is in the positive side, at least for a large composition range. Here it is in the negative side, completely convex now. Okay, so there are implications of this delta G mix curve looking like this. We'll see about that shortly, but this is what can happen with respect to temperature when this delta H mix and delta S mix, T delta S mix compete with each other. They eventually change how the Gibbs energy looks, and the Gibbs energy governs how the phases will form. So this is quite important. This is a case where delta H mix itself is negative, and minus T delta S mix anyway is negative. Adding both of them, we get a highly negative delta G mix. This can also happen. Now, what is this reference state in G versus X curve? So here we say this is delta G mix, let's say of some phase beta versus X. That is the curve here. This is a Gibbs energy of mixing for beta phase. Now this is Gibbs energy of beta phase versus composition. Of course, this when we say Gibbs energy, we should be using some reference state. Here that reference state is standard elemental reference. Actually, if you see this delta G mix, this is also nothing but Gibbs energy of beta with respect to a different reference state. That's all, right? So if you make this value as 0, if you make this value as 0, then this entire curve will become this mixing energy curve, right? So mixing energy curve delta G mix beta is in a way G beta only, but with respect to a different reference state. Okay, for example, consider beta is BCC. Okay, delta G mix beta is nothing but G of beta with the reference state of BCC for both A and B at the temperature T, whatever temperature we are considering. At this temperature, whatever is the Gibbs energy of A and B in BCC structure, it is made to 0. Therefore, we get the Gibbs energy curve as the mixing energy curve, nothing but the mixing energy. Okay, basically removing all the reference energy state values and getting only the mixing energy value as the G value. That's what it is. Okay, this exact thing will be used when we go for calculate softwares like thermocalc and all to calculate Gibbs energy of mixing. We are basically going to make the Gibbs energy of pure elements 0 at the temperature of our consideration. Okay. So if the G values of both A and B in BCC structure at T are assumed to be 0, that's what has happened in this case. Okay. So here if we bring another curve, G of epsilon versus a composition, and understand what is this, G of beta with reference state SCR for A and B, this is what we said. This curve is with the reference state SCR for both the elements, and consider this epsilon to be HCP. This curve is for the HCP phase. That is A is BCC and B is HCP at 298. Their enthalpy values are assumed to be 0. That is how these curves are drawn. You can see B for the B part, this epsilon curve point is lower than the beta curve, meaning epsilon is the stable state or HCP is the stable state for the element B. Okay. For element A, you can see the yellow curve is lower than the green curve. Therefore, beta is the stable state for element A. Okay. So when we say SCR, that's what we mean. What is the standard state for the element at 298 Kelvin, and at that temperature, whatever is the enthalpy, that is considered 0. That is the meaning of reference state SCR. Right. So we said we will understand the implications of these different shapes of the curves. Now you try to test your understanding. If we have this kind of curve for a phase, let's say gamma phase versus composition is like this. Is single phase stable at XB is equal to 0.3. So XB 0.3 is somewhere here. At that temperature, is single phase gamma stable? That is the question. Okay, think about that. How will you proceed with this? Stop, think about it. Once you are ready with the answers, then play. Okay, so at this composition, let us mark a point in the curve and put a tangent to that and check whether any part of Gibbs energy curve is below that. Okay, in fact, the entire Gibbs energy curve is below that. That means there is a problem. This is not the stable phase at that composition. Okay, so the answer is no. Single phase alpha gamma will not be stable at this temperature. So the answer is no. Single phase gamma will not be stable at this temperature and composition. What will be stable is something like this. You see, two phases of similar crystal structures, gamma will be stable from this composition to this composition. For this entire range of compositions, you will have two phases, one with this composition, other with this composition, meaning a very low amount of B, very high amount of B, two separate phases. Both of them have gamma crystal structure. They will be in equilibrium. That's what will happen for this entire range of composition. Point 3 is part of it. Okay, so definitely at point 3, these two phases will be stable. Of course, if you try to make this composition stable at one single phase, gamma with gamma structure, it will eventually decompose into two phases with a high B and low B. We also call it unmixing. If you try to make single phase, it will get unmixed. That's the meaning. So two phases of similar crystal structures appear because of this. So this is one two-phase equilibrium. We have also seen one more two-phase equilibrium like this previously, where we had two phases coming in equilibrium, but they have different crystal structure. In this case, it is alpha and phi, two phases of different crystal structures. They can come in equilibrium. So the two phases occur in different manner like this. But what is important here is, even in one single crystal structure, one single curve, you can identify the two-phase formation like this. Right. What about these Gibbs energy curves for compounds? Whatever we have been seeing till now are mostly solid solutions. What about it for compounds? And when we say compounds, we have two types, non-stoichiometric and stoichiometric. Non-stoichiometric can be an intermetallic phase with a large stability range or homogeneity range. It will have a Gibbs energy curve like this. Okay, and so for some big range, it will be stable. Okay, or an intermetallic phase with a narrow stability range. This is a narrow stability range. For a small composition range, this compound is stable. So in either case, there is some range of composition that is more important. Okay, so when we say non-stoichiometric compound, it is not having a single fixed composition, it has a small range of composition. So obviously, when we say stoichiometric compound, it's an intermetallic phase with a fixed composition. There is only a dot here. Okay, I'm putting some kind of a symbol here, but it is just a dot because only at that temperature, only at that composition, we have this phase stable. So Gibbs energy is given only for that composition. So this is how compounds Gibbs energies are. This compound, if we look at it little more carefully, how is the atomistic picture? It will have complete chemical order like this. A, B elements are in complete chemical order. Delta H will be extremely highly negative. So this is a stoichiometric compound, an intermetallic phase with a fixed composition. No randomness in chemical species in lattice sites. So there is no way to mix A and B. Okay, A is fixed in some position, B is fixed in some other position. They cannot exchange their position. So therefore, no chemical configurational entropy change is possible. So to understand the Gibbs energy of it, we have to start from non-ideal solutions Gibbs energy because delta H is not 0. This is what we have written for non-ideal solution Gibbs energy previously. But for a stoichiometric phase, it's going to change because this delta G mix ideal is not there at all. Delta S mix ideal is 0. Therefore, this term will vanish. We'll only have delta G mix excess. Okay. And now we are not talking about mixing of elements, we are actually talking about formation of a compound. Okay, since it is formation of a compound rather than mixing of elements to form a solution, instead of this delta Ge mix, we will use delta Gf, F for formation. So this delta Gf is Gibbs energy of formation. Fundamentally, these are same, you could understand. Basically, we are talking about excess Gibbs energy of mixing. Since it is a compound formation, instead of using the word mixing, we use the word formation. Okay, it's a small distinction that will help us. Right, so G versus X diagrams can be used for more application. For example, in this case, there is one solid solution and one intermetallic in equilibrium. A two-phase equilibrium of solid solution and an intermetallic phase can look like this. With this kind of construction, we will understand many ideas. Okay, so G versus X diagrams are useful to understand many more ideas such as driving force for nucleation, driving force for transformation, and quantitative stability competition of various phases, the ease or difficulty of achieving or suppressing certain phases by alloy design, the relative competition of factors in thermodynamic stability. All those things we will see as we go along. In the next class, we will focus on some of them. Right now, we'll do one clarification. Sometimes you see people think when we say criteria for equilibrium, Gibbs energy should be minimum. That is our ultimate criteria. But we also told chemical potential of elements must be same across the phases. Actually, these are same. In order to clarify that little more, I am putting few slides here. So in this case, whether equilibrium is there, is G minimum or mu equal, we'll see that. If I draw a tangent here and try to make only phi, try to consider only phi as the stable state, you know definitely it is not stable, because below this line, tangent line, there is some Gibbs energy curve. Therefore, only phi is not stable. And in this case, chemical potential of A in phi is here. Is it equal to chemical potential of A in alpha? No. Similarly, chemical potential of B in phi, is it equal to chemical potential of B in alpha? No, at this composition. So G is not minimum here. What is chemical potential of A in alpha and B in alpha? These are the values. Are they equal to chemical potential of A in phi and B in phi? No. Is the Gibbs energy minimum? No, because there is some other Gibbs energy curve which is lower than this. So in this case also Gibbs energy is not minimum. In this case, we know Gibbs energy is minimum and chemical potentials are same. Right? So this is what Gibbs energy minimization and mu equalization is. In this case, both are happening. Gibbs energy is minimum for this composition only at this two-phase equilibrium. Any single phase equilibrium will not make it minimum. Okay. So in this case, G is minimum. Right? So what happened is Gibbs energy actually dropped from here to here when we started making chemical potential equal across the phases. So Gibbs energy minimization and chemical potential equalization are same. So therefore, chemical potential of an element becoming equal in all phases in equilibrium is equivalent to saying Gibbs energy of the system becoming minimum. So this is what we are going to do when we go to determining the phase equilibrium. Identify the set of phases that either minimizes the Gibbs energy or in which the chemical potential of each element is equal across all the phases under given conditions. So in order to do this, we are going to use the computational tools. This procedure is called as Gibbs energy minimization. So we will see that in the future. Thank you. I hope the lecture is useful. See you in the next class.